Here is a combined summary of the 4 pages. The paper introduces a novel fermionic description of flagged k-theoretic symmetric polynomials, generalizing the author's previous works on fermionic descriptions of skew Grothendieck polynomials and multi-Schur functions. The flagged skew Grothendieck polynomial g lambda, micro, f per gram, x, is defined using the generating function and the determinant formula, which differs from the one defined in a previous work but coincides with it under certain conditions. The main theorem provides a fermionic description for the flagged Grothendieck polynomial, utilizing concepts from vertex algebras such as fermion-Fock spaces, vertex operators, and vacuum expectation values. The fermion-Fock space F is generated by the vacuum vector 0, and the dual Fock space F** operator is generated by the dual vacuum vector 0. An anti-algebra involution on the algebra A induces a linear involution omega F right pointing arrow F** operator, and the vacuum expectation value is a unique C-bilinear map that evaluates the expectation value of a product of vertex operators applied to the vacuum vector. The paper presents a comprehensive analysis of flagged k-theoretic symmetric polynomials, utilizing vertex operators and their commutation relations. The normal ordering of monomial expressions is defined in terms of psi n and psi * operator n, and the Hamiltonian operator h, x, and its dual h** operator, x, are introduced, along with the vertex operators eh, x, and eh* operator, x. The commutation relations between the vertex operators and fermion fields are discussed, providing equations that demonstrate how these operators interact with each other and with the fermion fields. The main result is presented in equations, where the flagged skew Grothendieck polynomials g, f per gram, n, x, are expressed as a series of fermion fields and vertex operators, providing a novel way to compute the flagged skew Grothendieck polynomials using the algebraic structure of the vertex operators and fermion fields. The paper notes the difference between two rings, C, Z, beta, and C, beta, Z, emphasizing the distinct properties of these rings in relation to the flagged skew Grothendieck polynomials. The paper introduces a novel approach to describe flagged k-theoretic symmetric polynomials using fermionic expectation values. A crucial relationship between the flagged Grothendieck polynomial and its fermionic description is established in equation 13. The main theorem, Theorem 3.2, provides a detailed expression for the flagged skew Grothendieck polynomial g lambda, micro, f per gram, x, in terms of fermionic expectation values, involving the use of two types of operators, a and b, defined in terms of input variables, z and wj. These operators are used to calculate the determinant of a matrix, representing the flagged skew Grothendieck polynomial, as shown in equation 16. The properties of the a and b operators are explored, with explicit formulas provided in equations 11 and 12. Revealing that they can be expressed as sums over flagged Grothendieck polynomials with coefficients involving powers of the variables z and wj. The operators satisfy certain recursion relations, further elucidating their structure and behavior. Utilizing Wick's theorem, the determinant in equation 16 is evaluated, leading to a new representation of the flagged skew Grothendieck polynomial as a sum over products of flagged Grothendieck polynomials, with coefficients determined by the variables z and wj. The research discusses the properties of flagged k-theoretic symmetric polynomials, focusing on their coefficients in relation to the determinant of a matrix. An equation for the coefficient of z lambda I minus iw micro j minus j in f, z, w, is presented, involving a complex line integral, which coincides with the residue of the differential form at t equals z. This coefficient is compared with the determinant, 16, to conclude the theorem. The paper also remarks on the case where parameters g1, g2, gr are all equal to 1, reducing the main theorem to a simpler form, which is further specialized to recover the fermionic presentation of the skew Grothendieck polynomial.